We've already looked at Boolean algebra operators, and we've seen those same operators in their digital logic gate form. We've also looked at how to utilize those operators with bit masks in code. Well, in this video, we're going to look at putting together those logical gates into larger circuits. We'll diagram those circuits out, and we'll find their equivalent Boolean algebraic expressions, and we'll calculate the output columns of their truth tables. So let's get started. What we're going to do first is just draw out some kind of simple circuit, and I'll talk a bit through how I prefer these circuits be drawn. So I'm going to make a simple two-input circuit. Let's say A is an input and B will be an input. Now we're just going to leave these symbolically, and when we make a truth table for something like this, we label the two initial columns A and B. Those are our inputs, and then we provide an output column. So instead of providing rows here with all the different combinations of the input, we're going to assume that a specific version of each of these variables is supplied in the form of a 0 or a 1, and that is bussed down these wires. All right. Now I'm going to make my circuit off here to connect everything from these wires, and we'll do something simple to start with. We'll use an AND gate, and I'm going to connect that AND gate to both. So we're going to have B coming in and A coming in. Now I like this style because all our input variables are bussed down on the left, and then we can follow the flow of data from left to right as much as we possibly can. Notice too that the lines coming into the AND gate that connect to the individual variable buses all have a dot. Now this dot indicates a connection, and it's important for your diagrams. If you don't have the dot, you will have something ambiguous, so we have to decide when a line crosses another line, is it actually connected. For example, it's easy enough here in B because this wire goes directly here and there's no other contact. But we're still going to put the dot even though it's unambiguous. From A, however, the connection from A is marked here with a dot, and then the wire actually crosses over this one with B. If this dot were not here, or we generally didn't use the dots, we may find ourselves in a situation where we are causing ambiguity in the interpretation of the diagram because of this crossover here. So we'll always use our connection dot. So far we have A ANDed with B, and I think what I'll do is I'll take the output of that and send it through an exclusive OR gate. Notice also I don't draw curvy lines to connect the output of one gate into another. I draw those always at horizontal or vertical lines, so the turns are all right angles. What else can we input? Let's input. I don't really know what this circuit is going to do, but we will find out. And just for kicks, let's get an inversion bubble at the end of the exclusive OR, which turns it into an exclusive NOR. And then we'll come out like this, and we'll label this wire X. So effectively what we have is a circuit for the function X, but we don't know what that function X does. So we'll have to calculate the truth table for it. But before we do, I want to take this circuit diagram that I've got here, this basic schematic, and I want to come up with the equivalent Boolean algebra expression for it. So the way we're going to do that is we're going to say that the function is X. And just like in your algebra class, remember when you did stuff like, f of x equals, 4x plus 2. You remember when you've done this in math class in the past? Well, we're going to use the same concept here. We're saying that f is a function of the variable x and is equivalent to whatever here is on the right, except we're going to do it with Boolean algebra. So this is the way you've seen before. We're going to do the same thing here. So x is a function of a and b. And the order for these is generally going to matter. So whatever order they show up here, we're going to put that here. Now, it's not that we couldn't put these in the opposite order visually and then redraw the circuit so that it's the same as a Boolean expression where these are listed in the A-B order. But when we get to one of our different Boolean algebraic forms, a shorthand form, it's really important that these be in order. So we're going to stick to that model straight from the beginning. So we're going to say x is a function of a, b, and is equivalent to, well, we've got a ANDed with b, and I'm going to try to keep my variables in alphabetic order. So a ANDed with b, even though I might see b coming down first. I'm going to say a ANDed with b. That's going to get exclusive OR, and exclusive OR is the circle with a plus with a. However, the output of that exclusive OR is then inverted, so we can just draw an inversion line over the top of this whole thing. So now we have a circuit diagram or a digital logic circuit for this function x, and we have the equivalent Boolean algebra function for x. Now what we're going to do is calculate its truth table. So I'm going to start with the input columns a and b, and having only 2 input columns, we are only going to have 4 rows of output, and we're going to label these. Remember that concept of min terms. So I'm just going to write mint. This is going to be row 0, then row 1, then row 2, and then row 3. And the 2 bits of input are going to be used to create the unsigned versions of these numbers. So 0, 1, 1, 0, 1, 1. That will always get us in the order I prefer. So 0 at the top, highest value, all ones at the bottom, and everything else is in numeric order. All right, so now we need to find out whatever A ANDed with B is. So let's calculate that in one column. We'll do this piece by piece so that we're more likely to be correct. A ANDed with B, well, since we're doing it directly on the input, we know that that's going to look like this. But if this had been the output of some other circuit, partial circuit ANDed with something else, we would have to carefully evaluate and say that it only produces a 1 when all of its inputs are 1. But in this case, it lines up pretty nice. So we've got A ANDed with B. Now we need to exclusive OR that with A. And so I like to make notations for this. So I've already used up A and B, and I've used up X. So I'm just going to call this subcircuit C. Then, when I make the next partial, I can write a smaller expression here, C exclusive ORed with A. Now at this point, I'm not just using the 2 inputs, so I can't just write 0, 1, 1, 0 as I would for a normal exclusive OR circuit on 2 inputs. Instead, I have to evaluate these 2 inputs and determine via the exclusive OR operation what bit should show up for each minterm row. So the way exclusive OR works, if you recall, is that we need one and only one of its inputs to be a 1 in order to get a 1. So I'm looking at the A column here and the C column here. 0, 0, that'll get me a 0. 0, 0, that gets me a 0. 1, 0, that gives me a 1. 1, 1, that gives me a 0. All right. So we're close now. Now I'll refer to this as D, just so I can have a shorter thing to write. Now I'm going to invert D because I need that expression inverted. And that's actually going to be equivalent in the end to our function x. So the inverse of D is just going to be 0 turns to 1, 0 turns to 1, 1 turns to 0, and 0 turns to 1. So now we have a circuit, a little digital logic circuit diagram. We have its equivalent Boolean algebra expression, and we know we've calculated its truth table, so we know exactly how this function performs for all of its possible input. All right, let's do that again for a slightly more complicated circuit. Let's see. We'll stick to 2 inputs again, though. So I'll say there's 2 inputs, A and B, and I'll bust these down. Let's do an OR gate, and I'm going to invert the input from B and get normal input directly from A. In fact, I'll do another one of these down here. And this time I'll keep B the same, and I'm going to put an inversion bubble here on my input that's connected to A. Don't forget your connection dots. And then I'll take the output of these two individual gates and run them together through an AND gate. Like so. And we'll call the output of that AND gate, we just used X, so we'll choose Y. All right, so we have a digital circuit. Let's take a moment and create the equivalent Boolean algebra expression. So we're going to have Y is a function of A and B and is equivalent to, well, let's get this top one in here. It's the OR of two things. It's the OR of A and the inverse of B. So that's A ORed with B that has been inverted. That's going to get ANDed with this other one, so I'm going to put this in parentheses. And because the two sets of parentheses will just be touching each other, we'll know that that's a Boolean algebra multiply or AND operation. So now I need inverse of A, or A inverse, ORed with regular B. I think that's it. Yep, that's it. So now we have our digital circuit, and we have the equivalent Boolean algebra expression. Let's find what the truth table has for the output of all our four inputs. We'll go with A, B, 0, 0, 0, 1, 1, 0, 1, 1. Now for this one, I'm going to be needing the inverse of A and the inverse of B. And whenever I see the inverse of an input variable used directly, not the inverse of an operation among input variables, but a direct use of the inverse of an input variable, I'll go ahead and take that input variable and calculate it out in its own column, just to make sure I've got something nice to refer to, again, to make fewer mistakes. So A invert is going to be where there's a 0, I'll have a 1. And where there's a 1, I'll have a 0. 0, 1, 0, 1, so that'll be 1, 0, 1, 0 for the inverse of B. All right, so then I need A ORed with B invert. So that is this column A and this column B invert. OR produces a 1 when when any of its inputs has a 1. So A has 1s in the bottom two positions, so we're definitely getting a 1 in the bottom two rows here. B inverse has a 1 in the 0th and 2nd minterm rows, so I have a 1 here, and, well, there's already a 1 there. Otherwise, this is going to produce 0. All right, now we're going to need the inverse of A ORed with B. Inverse of A ORed with B. All right, inverse of A. Again, it's an OR, so we look for 1s. 1 and 1 at the top, so we put those two here. Regular B has a 1 in row 1. We've already got that. And a 1 in row 3. So that goes here, and we'll get a 0 there. Now, we need to take these two terms and AND them together. So I'm going to call this C, and I'll call this D. And we'll say we get C ANDed with D here. Ooh, I should have used black for that. Breaking with my pattern. Oh well. And that's the same as the function Y. So let's see here. If we're ANDing two things together, we need both of the inputs, or all of the inputs, to be 1. So 1, 1, that gives me a 1. And 1, 1, that gives me a 1. All the other rows, therefore, must be 0. Okay, so this is a circuit that is randomly the inverse of exclusive or we should say this is the exclusive NOR circuit. It's equivalent to that, but we've used a bunch more gates. So we have our digital circuit diagram, we've got an equivalent Boolean algebra expression, and an equivalent truth table. All right, let's do another one. This one will use 3 inputs. We'll make this one bigger. And because it has 3 inputs, I know that the truth table will be larger, so I'm going to leave more space here at the bottom. and move the actual circuit higher up. This time I'm going to start with the expression itself. So let's say z is a function of a, b, and c. So we've got 3 inputs, which means we'll have 8, which is 2 to the third, 8 min-term rows in the truth table. And we'll say that this is equivalent to A ORed with C NORed, or inverted, ORed with the inverse of B and C, exclusive ORed first with A. Okay, so here's just some absurd Boolean algebra expression. So now we're going to go from this Boolean algebra expression that's more complicated in terms of the number of inputs, well, we'll go to the circuit diagram, I guess. Let's do that first. So here's inputs A, B, and C, and I'll bus all of them down. And what am I going to use for inverted? I need B inverted. Oh, no, I'm thinking truth table. Okay, so the first thing is A or C. So I'm going to put that here with its output inverted. So A or C. Now I'm going to put, I like to draw my connections. Like in this case, I'll connect C first. Even though it says A or C, you might think you just draw a line from A over. I like to make mine so that if you imagine the wires coming down, they kind of turn a little and go off to the side. So 2 wires come down and turn and go off to the side. So it's like a rainbow effect rather than putting A on top and C on the bottom. That's like a folded ribbon cable, and I don't prefer that method. So I'll connect the lowest or the later alphabetically first. So C is connected, and then A is connected. Don't forget your connection dots. And that's going to end up getting ORed with this mess. This looks long, so I better do it first. I need the inverse of B ANDed with C. So that's an AND. And it's regular C. And the inverse of B. So as B comes down, it gets inverted going into the AND. All right, that gives me part of this. That has to get exclusive ORed with A. So I'm going to add my exclusive OR here. And then this guy comes over to A. Beautiful. All right. I've got this whole thing, which now needs to be ORed with this thing. So we'll put an OR in. I guess I'll do it up here. Yikes, that's a little tight. But we can do it. There we go. And that produces our output Z. So we have started now with a Boolean algebra expression and gone directly from it to an equivalent circuit. And this circuit is a direct model of that expression right there. So we can get either one from the other. Now we'll derive the truth table. So we're going to have 3 input columns, A, B, and C. And now we need 8 rows because 2 to the third is 8. I'm going to start with the bit pattern for 0. Then we go to row 1. So this is the bit pattern for 1. Bit pattern for 2. Bit pattern for 3. 4, 5, 6, and then the final row is 7. All right. Separate my columns. Now I'm going to use the inverse of B later, so I'll go ahead and calculate that right away. The inverse of B. B went 0, 0, 1, 1, 0, 0, 1, 1. So the opposite will be 1, 1, 0, 0, 1, 1, 0, 0. Okay. Now, we also now are going to need A or C. All right, we can do A or C. We could do A nor C. as long as we think through it. And let's go ahead and do that. So when you OR two things together, the special case is that on all zeros for inputs, you get a 0 for output. If we invert that, that means when we have all zeros for input, we'll get as 1 as output and zeros under every other circumstance. So we're looking for all zeros to get a 1. A and C. Here's all zeros. We get a 1. A and C have a 0. We're going to get a 1. And we can't get any more down here because A is 1 all the time. So these are the only two that have A and C both being zeros. All right. That means everything else must be a 0 for output. Now that's going to get ORed with the inverse of B ANDed with C, exclusive ORed A. So let's do that in parts. Inverse B and C. All right, so it's an AND. I'm looking for double ones. Inverse B is here. C is here. Here's a double 1. And here's a double 1. And everywhere else is not. So we must have zeros in each of those midterm rows. Now we need to exclusive OR that with A. So I've already got A, B, and C. I'll call this, well, I'll have to reuse this later. So I'll call this D. I'll call this E for the sake of it. And then we are looking for E, that's this, exclusive ORed with A. All right. So exclusive OR, I need 1 and only 1 to be a 1. So they got to be mismatched. This is E, this is the A column. 0, 0, no good. 0, 1, good. 0, 0, nope. 0, 0, nope. 1, 0, good, a mismatch. 1, 1, nope, they match. 1, 0, 1, 0, good. These are both 1s in the output. So this we'll call F. And now we need to take F and OR it with D. So D or F. And in the end, that's going to be the same thing as our function Z. So D ORed with F. Wherever we see a 1, there should be a 1 in the output. So 1 for D here, 1 for D here, and nothing else on D. For F, there's a 1 here, a 1 here, a 1 here, and a 1 here, which means we'll have a 0 here and a 0 there. All right, so we started with a Boolean algebra expression, we converted that to its equivalent digital logic circuit, and we derived the truth table for this particular thing. And so where do we go from here? Well, there are some issues with this business that we did down here, right? In particular, this expression is kind of ugly. This is not a nice looking Boolean expression. It may exactly represent the logic that we need, but it doesn't appear to represent the logic we need in any meaningful way. Nothing about this Boolean algebra statement expresses that it produces a 1 all the time, except under the circumstance that we have A and C being 1s and B is a 0, or it's the circumstance where A is a 0 and B and C are 1s. Right? It doesn't express that precisely, so that's not good. A second issue is that that particular Boolean expression required us to make a relatively complicated truth table. I mean, it's not terribly complicated, but this is a tiny trivial circuit. If we were to do this with something larger, we're going to have larger truth tables, and in calculating that truth table, we're writing either a 0 or a 1 for gobs and gobs of rows and in one column and then move to another column that's based on that. Anytime we make a single mistake determining a 0 or a 1, that can have aggregate effects down the rest of the truth table. So neither of these are good. So in a future lecture, we will consider better ways to express individual Boolean functions that we want represented in digital logic.